Hello everyone, my name is Xiaogang Xu. Today I will present our paper, Low-Light Video Enhancement via Spatial-Temporal Consistent Decomposition. Well, this is the overview of our paper. In this work, we make two main contributions. The first contribution is a novel decomposition strategy designed for video data learning in the low-light enhancement task. The second contribution is a dual network for better achieving the consistent decomposition, avoiding expensive temporal pixel-wise alignment. We will introduce those two terms in details in the following. First, we make assumptions that a video can be decomposed into two parts, including the view-independent part that mainly aim to represent the physical property of objects, and the view-dependent part that aim to modeling the facts influenced by lighting conditions. Many similar multiplication-based decompositions exist, while ours is different from them, with new learning constraints. Moreover, our decomposition is designed for the video data, while current methods are mainly employed for image-based one. So we must consider the temporal consistency in the reconstruction term, and we also found that the consistency property can be utilized to constrain the view-independent and view-dependent parts. In other words, the video data can indeed guide the decomposition. For the view-independent part, suppose it is dominated by R, we can complete it as view-independent property by pursuing the same object in different frames to have the same content. As for the view-dependent part, which is dominated as L, we can assume that there is the continuous consistency in the corresponding videos. Moreover, we also require the multiplication of them can reconstruct the video. To complete the learning of RT, we first found some objects in different frames via finding the correspondence at pixel level among different frames. This can be done by using a current pre-trained correspondence estimation network such as DKM. And also the coordinate and the uncertainty will be returned. We can then constrain the aligned pixel-wise RT value to be the same. This can be expressed in this equation, where x1m and y1m is the pixel coordinate in the frame t1, and x2m and y2m is the correspondence in the frame t2. As for the loss term for the view-dependent part L, we employ a spatial smoothness loss, which will pursue the continuity in the temporal and spatial dimensions. Especially, the continuity change can be expressed by the gradient in both x and y axes, so we can use the L2 norm of them to represent the continuity. Moreover, we also note that different areas will have varying requirements. For example, in the very dark areas, the continuity is more hard to evaluate, so we set the pixel level weight for the smoothness constraint. Also, we need the reconstruction loss that is supervised with the video data. In this way, we can ensure R and L will have the required property and also can represent the video itself. Well, besides the new decomposition strategy, we also design a new network structure for low-light video enhancement. We think to enhance the consistency of the decomposition, it's critical for various frames within a video to share features. And to implement the share of features among different frames, we think design a cross-frame attention strategy and using simultaneous supervision for different frames. By incorporating shared features and simultaneous supervision, the features needed for synthesized decomposition parameters across different frames can have greater consistency. This is an overview of our network, where T1 and T2 are two randomly selected frames, and FD-T1 and FD-T2 are the corresponding features of the encoder. We can interact their features via such a framework to obey FD-T1 and FD-T2, which are then sent through the decoder to obey the prediction of L and R for each frame. Well, the interaction via cross-frame attention can be represented as those equations. First, we use different frames feature to serve as Q, K, V, And after obeying the attention computation results, we also use a fusion network to fuse them again, obeying the final result. In summary, the overall loss term for each batch will including the reconstruction loss for each frame, the view-independent and view-dependent constraints for each frame's predictions. Now we talk about the experiment. First, we conduct a comparison experiment. We choose SOTA low-light video enhancement method as baselines and conduct the experiment on several public datasets. The results are displayed in these tables, showing that our method achieves the best performance on those datasets consistently. Moreover, we also evaluate the performance in terms of temporal consistency. We're using the consistency evaluation in both short-term and long-term where flows in the videos are utilized. As we can see, our method can also achieve the best temporal consistency, avoiding the temporal flicking in those sets, showing the advantage of our method. We also provided the visual comparison among our method and other low-light video enhancement method, and we can see our method has the best enhancement visual quality. The same conclusion is also held in other datasets. Furthermore, we also conducted the experiments on different datasets, removing the proposed important components from our framework. The results show that the version without our proposed improvements will cause the degradation on. We conducted a large-scale user study for human subjective evaluation. The evaluation is completed via A/B tests among our method and baselines, which are decided based on the quality of synthesized images from different aspects. As we can see, our method's results are preferred by people. At last, we also evaluate the performance of our framework in terms of the robustness on the correspondence. We'll conduct two experiments. The first, adding the noise to the correspondence, and the second will reduce the number of correspondence. As we can see, although the performance is reduced, the results are until better than baselines, showing it as the robustness of our method. Thanks for your watching.